I'm so excited that you're all here today to hear a little bit more about our program. This is a really cool curriculum. I've been at Thayer for a long time, it's about 10 years now. And this program really highlights the human-centered design philosophy that we really embody at Thayer. It has all the characteristics of an in-person Thayer program. You will get time and get to know all of your instructors and professors really well. So I wanted to start out by talking a little bit about what I feel makes this program really special in terms of the curriculum. And the first point I alluded to a little bit earlier is that these courses are developed as one cohesive program. This is not 9 classes, each in an individual silo that are just grouped together because they share similar content areas. Your professors all know each other really well. They get along well. They're friends. And we work together to develop this whole curriculum. And so while I'm central, all of the professors in this program are working together to say, how does my class fit into this larger whole program that we're building? And that offers a lot of advantages because it means that we get to have through threads and cultivate certain skills that are really useful in developing intelligent systems, not just in one class, but from the very first class all the way through to the capstone in the program. And so you'll see recurring themes, particularly around like engineering design methodology, that will carry through from class to class, allowing you to build those skills over time. That's one area that I think this program really excels in. Another area is that this is really focused on lower level mechanics, the how and why of intelligent systems. And we'll see that as we look a little bit more about like what specifically are you going to be doing in each class. This is really about how do we get intelligent systems working in hardware. And that requires a deep understanding of both the low level mechanics of the mathematics of how do we develop machine learning models, but also of the how do we work with hardware and implement designs in hardware. And so you'll get both sides of that experience in this program. For our dedicated hardware courses, which there's 5 that are going to have a significant hardware component, we will, if you enroll in the program, we'll ship you a lab kit with all of the circuit components, lab test equipment, development boards, everything that you would need to build all of these things at home using the same kinds of boards that we would use in an in-person class. And finally, I think the last thing that sets this program apart is even though this is an online and largely asynchronous program, our courses feature an extensive amount of project and collaborative work. Your end of evaluation is not going to be some big final exam. We place a high premium on project work that's relevant to the things that are you might do in industry or in a later academic program. And we place a high premium on, we learn best when we can talk to each other about the work that we're doing. And so many of our courses feature term-long projects that are team projects where you're going to be working with your peers. And I think this is really important because this is a program that's designed for folks who are either freshly out of an undergraduate program and are interested in pursuing this area in master's, or for working professionals who might be and have 10 years of experience in their field or 20 years of experience in their field. We have a very diverse student body. And so when you're collaborating with your peers on these projects, you're really getting to know each other over the course of your time together as a cohort. And that brings a diversity and wealth of experiences that you'll learn from each other as well, in addition from learning from your instructors. So let's look a little bit about where do we begin the program. We start with sort of 3 foundational courses that are going to set you up well to explore both the sort of theoretical side of intelligent systems with deep learning models, for example, and the hardware side of things. And so looking at, for example, if you started in the spring, year 1, where we'd start out in our first 3 terms with machine learning, embedded systems, and signal processing. And these classes together really form the foundation that we will need to succeed in the program. So let's take a look at that first course, machine learning. Ken, do you mind going to the next slide? Thank you. Um, so our machine learning class is really cool because it's focused very much on the low-level fundamentals of why do these machine learning models work. This is not a class where we're going to come in and just boot up a bunch of like scikit-learn models and just get them running. This is really focused on the lower level mechanics. And so we'll explore a variety of different types of models but there's a heavy emphasis on understanding both the probability theory and the multivariable calculus that allows us to take, say, a generic neural network diagram and really break it down into what are the component parts, how do we work through this. And this is going to be really valuable because when we're going and implementing intelligent systems and hardware, we don't necessarily have a package that we can just install that's going to enable us to build the model automatically. We often are going to have to build things by hand, or when we're tuning models, we want to be able to draw on the intuition about like how do the underlying mechanics work that are going to allow us to create better models even when we are using those kinds of packages. And so this class really helps set up that sort of fundamental knowledge in each of these areas. We'll spend sort of 5 different sprints in this class looking at different kinds of fundamental machine learning model families, and have a sort of research-based course project that runs in parallel with that. And so that's going to set up sort of one pillar of the mathematical background that we need, but we're going to cultivate sort of a second pillar of our mathematical background in the signal processing class. And this class is really cool because it allows us to really engage with some of the complex mathematics that we need in order to understand a realm that might not be totally intuitive to us at the outset, the frequency domain. We often perceive things in terms of time. This is where we have a lot of intuition about the world around us. But many signals we can best understand by studying them in the frequency domain. And so this class is all about building intuition about how do signals, things that we might want to input to a neural network, behave. How can we better extract them through things like filtering techniques, like we can see here? One of our goals is by the end of this class to be able to effectively filter the signal from the noise. And so this class offers a slightly different perspective on the mathematics needed for doing this kind of work. And between the machine learning class and signal processing class, this is going to tie into pretty much all of the classes that you're going to look at throughout the rest of the program. This is where some of the starting through lines begin. We'll see ideas here get carried through all the way to the capstone when we're working with like medical applications. We want to be detecting very weak signals. We'll use these kinds of techniques that we established in these early classes in order to extract that. But there are a couple different endpoints of the program, as we'll talk about in a moment. This is also going to be relevant when you're looking at higher level classes like our applied natural language processing course, where we will use intuition that we build in signal processing to inform how we understand our models in those spaces as well. And so we've talked a little bit about the sort of mathematical pillars that we're going to be building, the probability theory and multivariable calculus that we'll gain in the machine learning course, and our work with complex numbers in the frequency domain that we'll see in the signal processing course, where we'll study things like the Fourier transform, the Z transform, the things that we need to really do good digital signal processing. Those are sort of two of the pillars, but this is also a hardware program. And so that leads us to our sort of third foundational class, which is going to be embedded systems. And so in contrast to the machine learning and signal processing courses, which are both feature Python very prominently, this course is all about how do we program embedded systems in C. And coupled with that, also building the fundamental knowledge that we need to be able to do embedded systems really well in both analog and digital electronics. And so one of the things that is really exciting about this program, right, is that this really sits at the intersection of many different interesting fields. And our student body is really diverse. Not everyone's going to come in knowing everything about these areas. So one of our goals in this program is if there's an area where you have less familiarity in a particular subject, to help build you up. And so here we'll be starting from sort of the assumption that, we're seeing some of these like analog electronic concepts for the very first time and helping to cultivate those skills such that you can build really interesting mixed signal systems where you've got code that's interacting with circuits. And so this, for example, is one of the microcontrollers that we'd be shipping you in your lab kit, with breadboarding and additional accoutrements that you'd need to go and be building up and testing these circuits in real time in your home or in your office. This class is also really exciting because it's going to help set us up for some of the later courses that are more advanced where we're going to be using the same kinds of components that we're seeing here. So that, for example, the microcontroller that we use in this course is the same microcontroller that we're going to use in the capstone. And this is just one of the ways that we're going to see a nice continuity and evolution as you progress through the program. that you're going to already have some familiarity with some of the tools that you're going to be using when you get to those more advanced classes. So let's just take a look and summarize sort of the last three, if you could advance to the next slide. These classes together really form the foundation for our program. And so this is primarily here for you to reference back to after the slides. But the big takeaways is that we're really focused on looking at things at a low level and using that to inform our intuition about how machine learning models work, how do signals behave, and how can we process them, and how do we design embedded systems, really with an emphasis on good design methodology and unit testing. And throughout this, well, the two primary programming languages, though we'll learn others as we progress through the program, are going to be Python and C. And we're really going to be building our fundamentals in those programming languages in these three courses. But you might be asking, where do we go next? So let's talk about some of the intermediate courses in the program, because we have some really cool stuff here. So one of the classes that you'll be able to take is distributed computing. And this is a really awesome class. Even though this is an online program, we are able to bring you to Thayer, to this labyrinth that we have set up through a live feed and the ability to remote into this lab. And so this class kind of is a continuation of some of the things that you saw in embedded systems, where we're going to be learning a language that's very similar to C called Go to manage distributed computing tasks. And this is a class that's a team project-based class. It's a term-long project-based class where your goal is to control a swarm of microcontroller-based robots to go and map a maze. And this is a really interesting problem because as you need to think about both how do we actually do the mapping, and then what happens when units start to conflict. And so we'll be thinking a lot about data integrity here, building off of ideas that we plant the seeds for in the embedded systems class. And you'll be interfacing a small cluster of computers remotely via Go that are going to be controlling these four robots. So you'll schedule like live time with the maze room and get to work throughout the term on improving your design and mastering some really key ideas that are going to be relevant to other courses in the program around concurrency and parallelism. Essentially, how do we take a really complex task and make it more efficient by having multiple agents acting in concert? So that's one of the intermediate courses. Let's take a look at another one. And perfect. Thank you. Um, So this is one of the classes that we're really excited about in the program. This is our advanced FPGA design class. And this has hooks into the distributed computing class because FPGAs are sort of like circuit playgrounds. They allow you with what are called hardware description languages to build arbitrary circuits on this integrated circuit. And that's really powerful because it lets us do things truly in parallel, which for very large machine learning models is essential because it allows us to speed up things like training and inference speed. And so this class is really special because FPGAs are pretty difficult to get into. There's not as big of a hobbyist community out there as there are for things like embedded systems or Raspberry Pi. This is one of the areas where you're going to be getting a lot of value out of the program because this is hard to get into. And part of that is that these kinds of hardware description languages often can buck our intuition. So we have a whole class that's dedicated to building up our fundamentals in digital electronics and understanding really good design methodologies for these tools that are becoming increasingly relevant for intelligent systems. We'll see FPGAs used in a variety of places where we care about flexibility of I/O, as well as really high processing speeds. FPGAs allow for true parallelism. And so, as we'll see when we get to later courses like our machine vision course, these are the kinds of things that are being used all over the place in a variety of really interesting applications. One of them you might have heard about in the news a few years back when NASA was doing its Mars Ingenuity helicopter missions. We'll study that as a case study in our machine vision course, but that used FPGAs as their sort of foundation to be able to autonomously navigate Mars, which is a challenging problem because they don't have GPS up there. FPGAs are one of the most promising areas in addition to things like GPUs for doing this kind of work. And so being able to do design is an incredibly valuable skill. Because this is an area that's often newer to students who enroll in our program, and because this work is challenging, we've written a dedicated textbook just for this class to work through and guide you as we do a term-long project that will incorporate elements from our previous classes. So there's a strong signal processing element because that's another area where FPGAs are commonly used, is enabling fast digital signal processing. And let's look at the third sort of intermediate course here that together with these other two are going to really prepare us for more advanced work in intelligent systems. And that is, of course, the ever important deep learning course. This is one of the few courses that has a prerequisite. We've designed the program generally to be largely agnostic to the order in which you take classes. And we've taken a lot of special care to do that well, such that courses complement each other. Because we know that one of the benefits of an online program like this is the flexibility. But this course has the prerequisites of the machine learning and the signal processing course. And this course is really about how do we do deep learning for structured data. And structured data, it could be time series data, it could be audio data, it also can be visual data. And this class has places a heavy emphasis on that kind of visual data where we're mapping pixels to a grid, and there's some structure that's imposed to that. Right? Pixels have meaning because they're near other pixels that might share similar characteristics. And so we'll explore a variety of deep learning models in this course. And the emphasis in this course really is on exploration and hyperparameter tuning. So coming to deeply understand and build intuition for how different key deep learning models behave, like LSTM architectures and recurrent neural networks, to convolutional neural networks and other architectures in these kinds of families. We'll also look at, for example, generative adversarial models, and we'll look at how do we generate images. So the images of the digits, the clothing, and the cats are all probabilistically generated images. These are not modified existing images. These are ones that are generated by the deep learning models that we'll be building in this class. And one of the things that's really lovely is that each of the courses, the course instructors get to bring in, their own backgrounds and expertise beyond the particular subject area. And M. Bergen, who is absolutely lovely, has a background applying deep learning models to problems in biology. And so we'll also spend a little bit of time studying how these kinds of deep learning models, like graph neural networks, for example, can be applied to study proteins better. And so these are the kinds of things that we'll be doing in these intermediate courses that are going to help us build the foundations for what I consider to be the three endpoints for our program. So to summarize, in these classes, we're looking at furthering the engineering design methodologies that we began studying in the early classes to build some more of the advanced skills that we need to really elevate the kind of work that we can do. And these courses allow us to really start, excuse me, exploring and fleshing out our knowledge. We'll be looking at more tailored programming languages like Go, like VHDL as a hardware description language for FPGA class, and then continuing with looking at now how do we use higher level Python packages in our deep learning course to implement these models, leveraging the fact that we spent time looking at how do we build these by hand in the machine learning course. And so let's look at the final three courses, which I consider to be our program endpoints. So the first course is going to be our natural language processing course. And this follows a track that is pretty direct from our signal processing machine learning course into our deep learning course, and now finally to this applied natural language processing. Let's take a look at some of the kinds of things that we're going to be doing in this class. This class covers a variety of topics. Ken, if you don't mind going to the next slide. The emphasis here really is on the application. And so we'll explore a wide variety of natural language processing models and techniques in this course. And each week we'll be looking at a different subset of this field and looking at what's the state of the art. How are people doing this best? and really looking at how can we take those packages, get them online, and adapt them to solve specific problems that are relevant to us. In parallel to that, there's a team term-long project that you'll complete where you'll build a fully fleshed out natural language process system. This term, teams are doing information retrieval, querying, and document summarization for financial documents, for example. Um, Throughout all these courses where we're looking at collaborative team projects, and the deep learning class has team projects, our distributed computing classes team projects, our machine learning courses team projects, all of these are going to be facilitated through Git. And we will provide you online tailored custom-built Linux images to complete your coursework in. And we'll teach you the fundamentals of Git that you need to really collaborate well. No, let's go on to the next slide, Ken. That's great. So that's one endpoint. In that natural language processing course, we'll look at a variety of things like machine translation, text to speech, speech to text, um, automatic speech recognition, parsing, vector embeddings for documents, topical and sentiment analysis, a whole variety of topics, and of course, the thing that many people associate with intelligent systems, large language models. Um, and that's one endpoint is sort of the text-based world in which we live, where these kinds of techniques can be very useful to us. But a different endpoint of what we can do with the skills that we cultivate in this course is looking at machine vision topics. And this draws on a larger web of courses here, where in addition to the signal processing, machine learning, and deep learning sort of core, we factor in elements from distributed computing in our FPGA design class to study machine vision in a variety of applications. So Ken, if you don't mind going to the next slide, please. And this course, again, we really want to build these courses in the program with a nice continuity. We're going to be using the same exact FPGA development board, this time instrumented with a camera to do real-time machine vision work. And this course blends both a deep understanding of the lower level hardware mechanisms that enable machine vision alongside case studies and weekly, excuse me, weekly design challenges as well as a group final project where you'll be looking at the system design for an autonomous vehicle. And we'll be throughout this course looking as well at the ways that advances in machine vision begin to pervade our lives. And so as an accompanying through line in this course, we spend a lot of time thinking about ethics. And some of the, as Dartmouth is a liberal arts institution, some of the literature and ongoing discussion around surveillance and the ever-growing instrumentation of cameras in our world. And so this forms another endpoint. You can see how this is a bit different than the kinds of things that we study in the natural language processing class, which tend to be more LLM based. The machine vision class is looking at how can we use these models to accomplish a wide variety of tasks in industry, in agriculture, for things like autonomous vehicles. And those two are distinct endpoints, which lead us to sort of a third endpoint for the program, and this is I would argue, the furthest endpoint, the Capstone, is a term-long project on smart sensors that has a focus on medical applications. And I'm really excited about this class because I think it helps demonstrate just the power of these kinds of techniques. That this course is looking at designing a mobile device that's able to analyze electrocardiogram signals. And it's doing that with a development board that costs about $25. This is a interesting problem because it's a term-long project where you're going to be working in an extremely resource-constrained system, which is part of the reason why it's so valuable to be able to know how to implement machine learning models by hand, is when you really need to squeeze every last little bit of optimization out of a system. And I think this really speaks to why these tools are powerful is it allows us to better democratize things like access to high quality, accurate medical equipment. And so, Ken, if you don't mind going to the next slide. Here, you're really going to be drawing on everything that you've learned throughout the program, the engineering design methodologies, the signal processing and machine learning fundamentals, along with the embedded systems skills that you cultivated way back at the beginning of the program, drawing in everything that you've done to build this one device. And again, we're going to be using the same microcontroller that we used in the embedded systems class to do this. This is really about looking at how do we make the systems design decisions that we need to make in order to do this well. And then when we're working in a resource constrained environment, how do we make the right trade-offs in order to achieve optimum performance? And this is a really cool class. We've got students in it running for the first time now, and they're really enjoying it. And so these are the sort of 9 classes that comprise the program and what we're going to be doing in it. Can you mind advancing to the next slide? So as we reach sort of the end, we kind of have these 3 different endpoints. The natural language processing, we're going to be looking at all sorts of different applications that are bleeding edge in this space. And of course, our large language models, having built the foundations to really understand how those are working. We look at our machine vision course, where we're really emphasizing the Thayer human-centered design methodologies, and system integration skills to create really complex machine vision systems. And then finally, the Capstone, which is all about resource-aware design, and tying together the skills that you've learned throughout the program. Um, and so these are what we're doing in the individual classes, but I just wanted to highlight a couple of the things that are shared between all the classes that I think are really an opportunity for students who enroll in the program and bring a lot of value to what you can do after you complete these classes. Um, so the first is that, right, we know that this is an area that is rich with ethical considerations, from environmental considerations to questions about data security and privacy to safety. Um, this is a program that's not just about being able to do the work, but preparing you to really lead in these areas after you've completed the program. And to that end, ethics is something that features very prominently in this program. And these 5 classes in particular invest the time to wrestle with some of these ethical questions with your peers and really get into them and think about not just, what do we do from a policy perspective, but really targeting the kinds of ethical questions that we as engineers need to answer. And then throughout all this, augmenting that with human-centered systems design practices and methodologies that are going to allow us to try to navigate these ethical hazards as best we can. Another aspect of this is that this is a program that offers you the opportunity to do significant hardware development. And this is not just a trivial component or sort of an extra bell and whistle to the program. You'll be spending a lot of time working with hardware with the various development boards and testing equipment that we are sending you in your lab kit. 5 of the 9 classes feature a significant hardware development component. And that's really powerful. Ken, if you don't mind going to the next slide, please. Because it gives you experience working with a wide range of devices, that you're not just gaining expertise in one particular niche, but that you're going to be comfortable working with, a wide variety of not just one microcontroller, but many different types of microcontrollers. You're going to have experience with FPGAs, which is really prized and is going to give you a deep understanding fundamentally of how digital electronic systems work. You'll also get exposure to working with, digital and analog circuitry along with power electronics, and then critically test equipment. So knowing how to use an oscilloscope, a function generator, and a logic analyzer to debug a system is incredibly valuable for actually building, intelligent systems efficiently. Any system of sufficient scale, particularly ambitious systems like these, are going to have bugs. And so that's one of the things that you'll become very good at, is not just getting these systems working, but getting these systems working efficiently. And Ken, do you mind advancing to the next slide? You'll also gain a wealth of programming experience. In addition to the hardware, we'll be spending a lot of time with Python and C, but you'll also be getting exposure to MATLAB C++ and Arduino, Go, and then VHDL for programming the FPGA. And then in complementing that, you'll spend a lot of time working with Linux systems and learning how to use Git to collaborate with your peers throughout the program. Um, Finally, we have place a significant premium on working together. Uh, Even in classes that don't have a significant collaborative project, we really encourage these classes to be social classes because the Thayer philosophy is that we learn best when we're learning together and talking to each other about the work that we're doing. These 6 courses in particular all have meaningful projects, many of them term long projects, where you're going to be collaborating with your peers, working on teams of anywhere from 2 to 5 to accomplish specific design tasks. And I think that this is a real strength of the program because, again, the students in our program come from such a rich diversity of backgrounds and have such different experiences in this very broad area. And so you really get to know and learn from each other in addition to from the faculty. Um, and so to summarize, what makes this program special, I think it's that looking, Ken, if you don't mind going to the next slide, going back to where we began, that this is a program that was designed with intentionality to give you everything that you need to be able to really design intelligent systems well. And that comes from spending time mastering the low-level fundamentals and then working our way up through design hierarchy to accomplish more and more ambitious projects. You will have the opportunity to meaningfully engage with hardware and build things that if you were bringing it to an interview, you could put it on someone's desk and say, "Hey, I built this. This is a really cool system. I want to tell you about it." And that you get experience with all those boards. You get to keep the kit after the program is done. This is your now development toolbox. And finally, that you will get to work and with and know your peers very well by the end of the program, and that you will get to spend a lot of time working on substantive projects that allow you to really hone the skills that we try to cultivate throughout the program.